So there are two short little topics we're going to look at today, not really having much to do with each other, but we'll tie them together over the next couple days. I want to start by going back to what's labeled as section 6.4 in your book and talk about arc length, or the length of a curve. For starters, let me give you a definition and a formula. Given a function, f of x, that needs to be continuous and differentiable on an interval. That is continuous and differentiable on some closed interval from a to b. The arc length, the length of that curve, is given by L equals the integral from a to b of the square root of 1 plus f prime of x squared dx. This formula will calculate the length of a curve that we have. We're going to see later where exactly it comes from. It's not a very involved proof, but I first just want to show you some examples of how to work with this. Usually we're just going to do this calculation on the calculator using f and int. I do, just for fun though, want to show you one by hand. For example, I want to find the length of the function y equals 4 root 2 over 3 x to the 3 halves minus 1 over the interval from 0 to 1. And I realize it looks like a very messy function. I actually chose it because it will become much, much nicer when we start to go do our calculations, and we can deal with this by hand. If we went to the calculator and graphed this, we would get a graph that looks something sort of like this. And I want to find, well, the length along that curve. Eventually where we're going to end up is we're going to start talking about two-dimensional motion rather than just along the x-axis anywhere on the coordinate plane, and we can find total distance traveled by using this idea. That's in a couple days. Right now I just want to go and try to use my formula. Well, to be able to use that formula, I first need to find f prime of x, or y prime. I'm going to get 4 root 2 over 3 times 3 halves x to the 1 half. And simplifying this, those 3's cancel, the 4 and the 2 cancels. I'm going to get 2 root 2 x to the 1 half. Actually, why don't I say 2 root 2x might be a little bit nicer to work with that way. Now, when I go to use my formula, I'm going to get L, the arc length, equals the integral. Well, over the interval I'm dealing with, so I'm going to integrate from 0 to 1 of the square root of 1 plus that thing, 2 root 2x, in parentheses squared, dx. Okay, I'm going to go clean this up a little bit. L equals the integral from 0 to 1 of the square root of 1 plus 4 times 2x, that's 8x dx. And this one, well, we can calculate this one by just doing a use substitution. Actually, why don't you take a moment, maybe pause the video, go do your use substitution, and integrate that thing. should get a length of 13/6. This wasn't a terrible integral, but usually these things are going to get very messy. So we're going to set things up by hand, but then just go to the calculator to evaluate most of these things. I want to show you just a couple more. Again, we'll use fn int. Then I'll show you where the formula comes from, and then we'll review a little bit of some pre-calc stuff. So let's take a look at y equals sine x minus cosine x. How about x cosine x, actually? And I want to deal with this between 0 and pi. And I'm going to save you the time of going to the graphing calculator and graphing, although we probably should look at what these things look like in general. It's going to be something sort of like that. And I want to find the length of this curve. My formula says L equals the integral from 0 to pi of the square root of 1 plus, okay, so the derivative of that thing squared. Let's see, derivative of sine x is cosine x, minus, okay, product rule on x cosine x. First, x times derivative of the second negative sine x, plus second cosine x times derivative of the first is times 1. Close both sets of parentheses and square this, dx. I mean, I guess at this point I could go to the calculator, but if I can simplify this, it's going to make the calculation easier on the calculator. So let's see. L is the integral from 0 to pi of the square root of 1 plus, okay, cosine x. Distribute that negative, but the double negatives will turn that into x sine x minus cosine x, that thing in parentheses, squared, dx. Actually, that's kind of nice. The cosines cancel. I'm just going to end up squaring that, which I think I could probably handle. I'm going to get the integral from 0 to pi of the square root of 1 plus, let's see, x squared, sine squared x dx. At this point, go to the calculator. Make sure you're in radian mode, and use fn int to evaluate. Remember, for the sine squared x, you've got to type it in as sine x, that thing in parentheses, with the square on the outside of it. And I'm getting about 4.698 for my arc length over there. Let me show you one more. What if we were looking at the function f of x equals 1/2 e to the x plus e to the negative x, and I want to deal with this between -3 and +3. I think before I do this, I'm just going to go and calculate my f prime of x. That's 1/2 times, okay, derivative of e to the x is e to the x. Derivative of e to the negative x is e to the negative x times -1. Good enough for now. This is going to be the integral from -3 to 3 of the square root of 1 plus 1/2 e to the x minus e to the negative x. That whole thing needs to get squared, dx. I mean, it's fine to go into the calculator like that. I might do a tiny bit of simplifying just because I can. 1 plus 1/4 times e to the x minus e to the negative x squared dx. Go to the calculator, do your fn int, and let's see what you can get out of this. Just be careful with some parentheses. Let's see, 20.036, I believe. Let me quickly show you where the formula comes from, just because, I mean, I probably shouldn't just give you some random formula. I probably should try to make it a little bit meaningful. So, the proof of the formula. Proof of the formula, L equals the integral from a to b of the square root of 1 plus f prime of x squared dx. Here's the idea. I've got some arc, and I want to figure out the length. Well, I don't really know how to measure the length along an arc, but I can measure the length of a little line segment. So let's say I put a little line segment here, then another there, and another there, and another there, and these are really tiny little line segments. But if I can find the length of each of those and add those up, I'll basically have the length of my curve. So let's say we have a small bit of our curve that looks kind of like this. Well, I'm going to approximate that bit of the curve by using a line segment. Not a bad approximation. Well, as far as this line segment goes, horizontally, it's moving some amount, I'm going to call it delta x, and vertically it's moving some amount, delta y. If I want to figure out the distance over there, well, I can just use Pythagorean Theorem, and I can say delta x squared plus delta y squared, take the square root. And that gives me one of my little arc length pieces, little segments I'm using to approximate my arc length. And if I add them all up, I'm going to get the total arc length, which doesn't really look like my formula. So I have a little bit of work to do. Let me go through a little bit of algebra here. Let's say I take that square root of delta x squared plus delta y squared, and just for fun, I'm going to go and divide it by delta x and multiply it by delta x, which of course is really just like multiplying it by 1. It doesn't change things. But I have the delta x at the end because I want like a dx when I'm done with everything. And let me just keep going with this. This delta x, I could put that under my square root as delta x squared. And I can say delta x squared over this thing under my square root would be like another delta x squared. Then I have delta y squared. I'm putting that under the square root delta x squared over there with my delta x at the end. I can simplify these things. This is like saying the square root of 1 plus delta y squared over delta x squared. That's just like delta y over delta x, that whole thing squared, and these deltas are like our d's. This is really like saying dy dx squared. The delta x at the end is like a dx. That's the length of one of those little segments. How do I find all of them? I add them all up by taking an integral. You integrate that thing from a to b, you're going to get your arc length. There are going to be a few things in the homework that look at that. Next thing I want to do is review something that you looked at in pre-calc. Actually, I think you might have even looked at this for the first time in Honors Algebra 2. I want to quickly review parametric functions with you. And then we're going to spend the rest of the year really doing some more work with parametric functions, some calculus with them, some particle motion stuff, and all that. In the textbook, what I'm about to do corresponds to section 9.2, parametric functions. To give you an example of a parametric function, something that looks like this: x equals t minus 2, y equals t squared. And I'm telling you t is greater than or equal to 0. This is an example of a parametric function. Our independent variable here is t, which usually stands for time. And at any particular time, we can calculate an x coordinate and a y coordinate for a particular curve. Eventually, we're going to move to the graphing calculator, but I want to try to graph this first thing by making a table of values and doing some plotting here. Let's see. I'm going to go horizontally with these things. I'm going to plug in a particular t, and I'm going to get out an x and a y. I told you that t was greater than or equal to 0. If you go plug in 0, you're going to get an x coordinate of 0 minus 2, negative 2, and a y coordinate of 0 squared, 0. You know what, while I do this, why don't I go and try to graph this thing? Maybe. At time 0, this function is at the point negative 2, comma 0. So I'm going to put a point over there. When t equals 1, we're at, well, let's see, our x value is 1 minus 2, negative 1. Y value is 1 squared, 1. So that's the point negative 1, comma 1. At time 2, this graph has coordinates, let's see, 2 minus 2 is 0. 2 squared is 4. So 0, comma 1, 2, 3, 4. Plug in 3. 3 minus 2, that's 1. 3 squared is 9. So at 1 comma, let's see, 4, 5, 6, 7, 8, 9. I think I'm going to stop there because I know if my y coordinate gets higher, it's going to be off the grid that I've had. I'm going to connect these. And there's a little bit more to it than this. I also need to show the direction that I'm moving along this curve. So I'm going to put a little arrow over there, maybe another one over there, to show that I'm starting here and moving in this direction. I don't see my particular times 0, 1, 2, 3 anywhere on the curve. That's just another variable that helps us find our x and our y coordinates. I'm hoping this is looking a little bit familiar to you. Let's do one more by hand, and then we'll move to the calculator. Let's look at x equals t squared minus 4, and y equals t over 2. And I'm going to tell you negative 2 is less than or equal to t is less than or equal to 3. Actually, why don't you take a few moments, pause this video, and see if you can go make your table of values. I'm going to make my t's negative 2, negative 1, 0, 1, 2, 3. Do some plugging in. And actually, see if you can do the whole graph. Plug in and go. Pause this and go. Negative 2 squared is 4, minus 4 is 0. Negative 2 over negative 2 is negative 1. Negative 1 squared is 1, minus 4 is negative 3. Negative 1 over 2 is negative a half. 0 squared is 0, minus 4 is negative 4. 0 over 2 is 0. Oh, let's see, 1 squared is 1 minus 4 is negative 3. 1 over 2 is a half. 2 squared is 4 minus 2 is 0. That is 1. 3 squared is 9 minus 4 is 5. 3 over 2, 3 halves. Let's see here. I have 0, negative 1. That's where I'm starting. Then it goes to negative 3, comma, negative a half, so maybe about there. Negative 4, comma, 0 is over there. Negative 3, comma, a half, about there. 0, 1 is like that. 5, comma, 3 halves, about there. And connecting the dots, it's going to look like that. So I'm going to start by going in that direction, then that direction, and ending over there. And that's what this parametric function looks like. I hope you don't have a problem with me calling it a function. I realize it doesn't pass the vertical line test, but that's not actually the point over here. The point of a function is you plug in a specific value and you get a unique output. Here, my inputs are specific t's, and my output is a coordinate, an x comma a y. So I plug in negative 2, I only get out the coordinate 0 comma 1. It's not like plugging in negative 2 gave me 2 different coordinate outputs. So even though it wouldn't pass the vertical line test, we can absolutely still call this thing a function. Last thing I want to do is just show you how to do a little bit of this on the calculator. I don't know if this is going to work, and if not, I'll bring up the calculator on the computer. Let's see what I can do here with this. Let's try to sketch, using the calculator, the parametric function x equals 2t plus 3 and y equals 4t minus 3 over the interval 0, 3. Okay, I don't know what's going to happen, but let's see. You probably can't see that so much. I bet I have my other calculator though. 1 second. Maybe. Oh, good. We'll see how long the batteries last. First thing I'm going to do anything parametrically is I'm going to change the mode on my calculator. Go down to where it says Function, Parametric, Polar Sequence, and select Parametric. This is not going to work. I need to go get new batteries. This is fun. I can't pause this, or I'm going to have to... Okay, you know what? Just hold on a minute. I'll be right back. Sorry, I can't pause the video, and if I stop it and have to put 2 videos together, something that would normally take like 5 minutes to upload to YouTube takes like an hour to do. So I apologize. I'm going to change the batteries on my calculator. This will be fun. Oh, goodness. Okay. All right, let's try that again. Sorry for that little interruption. I want to try to graph that function on the calculator. You're going to push mode. You're going to change the mode to parametric mode. And then you're going to push y equals. And instead of seeing like normal y equals, we see x equals and y equals. In the x equals, I'm going to type in 2t plus 3. I'm going to say 2. And if you use your x, t, theta, n button, because we're in parametric mode, if you push it, it's going to give you a t, which is exactly what we want. Then I'll say plus 3. As for the y one, I'm going to say 4t minus 3. Again, just use your x, t, theta, n button. You're going to get a t out of that. Before we graph this, I want to set my window. In addition to the normal x values and y values, which I'll leave at negative 10, 10, 1, negative 10, 10, 1 for x min, x max, and the scale, I need to tell the calculator what to do with the particular t's. Well, because this problem was dealing with between 0 and 3, I'm going to make my t min 0 and my t max 3. T step is basically how it's going to create the table of values to do this. It's a random number right now. But if I make my t step like 0.1, it's going to go and plug in 0, then 0.1, 0.2, 0.3, 0.4, up to 3. It's going to plot 30 points. Maybe that's not good enough. I'll adjust if I need to, but I think it's going to be okay. I'm going to go push graph and see what this looks like. Yeah, actually, you know what? Just for fun, let me try to make my t step a little smaller than 0.1. How about I make it like 0.01 might be too much. It might take the calculator a little while to do this, but let me see what happens if I make it 0.01. Oh, that's not too bad. And I'm getting a curve that looks something like this. When you sketch this on your paper, really just kind of copy what you're seeing there, and just make sure you include little arrows showing you were starting here, and it's going to there. Let's do one more. Let's sketch x equals cosine t, y equals sine t, and let's do this between 0 and 2 pi. So I'll change my x1 to say cosine t. I'll change my y1 to say sine t. T minimum 0, T max 2 pi. I could make T step 0.01. Oh goodness. The phone's ringing. And I'm going to ignore that, I think. I think I can leave the T step at 0.01. I think that's okay. I could do some fraction of 2 pi, whatever. This will be good enough. I'm going to go to graph it. It's a little tough to see. It's moving kind of slowly. Actually, it looks like it's tracing out a circle. And actually, this parametric function really is the parametric function that gives us the unit circle. If it's easier to see, why don't I change the viewing window a little bit? Let me go from like -2 to +2 for the x's, and same with the y's. We want to do a sketch of this. Getting something like this and like that. And we've got a circle. Wonderful. I'm hoping this is kind of a review from last year. If not, I hope you see what's going on with these things. And then next class, we'll start getting into the calculus of parametric functions. I have some curve here. I should be able to find the slope of it, the concavity, and all that sort of stuff. We'll deal with that next time.